Today, we're diving into something truly mind-bending, the incredible intersection of artificial intelligence and neuroscience. We're going to explore how scientists are starting to not just read, but actually predict the thoughts firing inside our own brains. It's a huge deal. I mean, just think about that for a second. What if we could actually see a thought forming, or a decision being made, moments before you're even consciously aware of it? It honestly sounds like something straight out of science fiction, right? Well, that exact question is what's fueling a massive revolution in brain science today. And the absolute key to unlocking all of this? Well, it's artificial intelligence. Researchers are now using AI to go way beyond just looking at the brain. They're trying to understand its fundamental operating system, to basically decode the very algorithms that create thought itself. So with a challenge this huge, where do you even start? Well, like any great exploration, the first thing you need is a map. You have to see all the parts and, crucially, how they're all connected before you can understand how the whole thing works. Here's a great way to think about it. Imagine the brain is this massive, bustling city, and our thoughts are the cars moving through it. The very first thing you'd need to do is map out every single street, every avenue, every little back alley. Without that blueprint, trying to predict traffic patterns would just be a complete shot in the dark. And in the world of neuroscience, this map actually has a name. It's called the connectome. And it is exactly what it sounds like, a complete, totally exhaustive wiring diagram of the brain. We're talking every single neuron and every single connection between them. It is the ultimate hardware blueprint for the mind. Okay, so this is really cool because it shows the two main strategies scientists are using. On one side, you've got projects like Flywire, which managed to map the entire brain of a fruit fly. A complete end-to-end diagram. That gives us the full picture of a simpler system. But then on the other side, for our own incredibly complex brains, you have the HO1 project. They mapped just a tiny piece of our cortex, but in absolutely breathtaking detail. Both are so important. One gives you the big picture, and the other reveals the mind-boggling details of our own wiring. And just to give you a sense of the scale we're talking about, that tiny little fragment of the human brain, it generated a data set of 1 petavoxel. That's a quadrillion 3D pixels. To try and wrap your head around that, it's more data than every movie you could possibly watch in your entire lifetime, all from a piece of brain tissue smaller than the head of a pin. It's just staggering. All right, so we've got our maps. They're incredible. But a static map is really only half the story. The real magic, the part that gets us closer to understanding thought, is when we use that map to predict action. We're going from the blueprint of the streets to predicting the flow of traffic in real time. So let's jump back to our city analogy for a second. Having the map is great, but what we really want to know is where a traffic jam is going to happen before it even starts, right? Or which route a car is most likely going to take. In the brain, that translates to predicting which neurons are going to fire and in what order. And believe it or not, this is exactly what projects like ZapBench are doing. The process is so cool. First, they basically take high-speed videos of a living zebrafish's entire brain, capturing the activity of all its neurons over time. Then, they feed these enormous video files to an AI model. The AI just watches these movies of brain activity over and over again until it starts to recognize the patterns, the rules of the brain's traffic, and then it can actually start predicting what's going to happen next. And the power of this is just wow. We're not talking about predicting 1 or 2 neurons here. The AI from the ZapBench project can predict the future activity of about 70,000 neurons all at the same time. We are literally watching an AI learn how to anticipate a living creature's brain activity. It's pretty wild. Okay, mapping a fly brain or predicting a fish's neurons is a massive leap forward, but it brings up an even bigger question. Are there fundamental rules of intelligence, some core principles, that apply to all brains, including ours? You know, that's the next great ambition here. And this has led to this idea of foundation models for neuroscience. A good way to think about it is like the large language models that run modern chatbots. The goal is to build a core AI that understands the basic language of neurons, which you could then fine-tune to understand a specific fly or a fish or, maybe one day a specific person. So how do you even begin to test a theory that's supposed to be universal? Well, you don't just jump straight to the most complicated thing you can find. In classic scientific fashion, you start small. And in neuroscience, a favorite starting point is the C. elegans worm, which has a tiny brain of just a few hundred neurons. And this quote right here, it really nails the whole strategy. I mean, think about it. If your universal model of intelligence can't even get it right for the simple electrical pulses in a worm's brain, there's no way it's going to work on a human brain. So the worm becomes this perfect, manageable test to see if your big idea is even on the right track before you scale up. Wow, we've covered a ton of ground here, from making these insanely detailed maps of the brain's wiring, all the way to using AI to predict what those wires will do in real time. So what's the big picture? Where is all of this heading? So let's do a quick recap of the journey we just took. First, we mapped out the physical structure, creating the blueprints. Then we used those blueprints to predict the dynamic activity, that traffic of thought. And now we're trying to model the underlying rules of that traffic, searching for the universal laws of intelligence itself. And really, this is the most important takeaway. For hundreds of years, we've basically been stuck on the outside looking in when it comes to the brain. But now, because of these incredible AI tools, we are right on the edge of a massive shift. We're going from being passive observers to becoming active translators, finally learning to speak the brain's native language of electricity and chemistry. Which, of course, leaves us with one last huge question to think about. As we get better and better at decoding all these neural processes, we can't help but come face to face with this really deep philosophical idea. If our thoughts, our feelings, our very sense of who we are, if all of that can be described as an algorithm, what does that ultimately say about the nature of consciousness itself? That's definitely something to chew on. Thanks for joining me.